Hi, really nice to be back here again talking to you. I'm going to give you a brief introduction to our technology and then talk through the improvements we've made on our platform. So our goal as a company is to enable the analysis of anything by anyone, anywhere. We are a technology platform that enables you, the Nanopore users, the community, to analyze anything, anywhere. And hopefully some of the improvements we're going to showcase to you over the next hour or so will enable you to push the boundaries of your science. So a quick run through on Nanopore sequencing. How does it really work? Well, you obviously have to start with a sample and extract your DNA like any other platform and adapt that DNA into a form that can go onto the Nanopore sequencer. And to do that, we have our Nanopore adapters, which are part of our kits. It has a leader to thread into the Nanopore, a tether to lower the input amount, improve the sensitivity, and a molecular motor that helps control the movement of the DNA through the pore. Once you've adapted your library, it goes onto a flow cell. That flow cell, as you might expect, contains a nanopore, highlighted in blue in this cartoon. That nanopore is sitting in a synthetic membrane material, which separates two electrodes. When we apply voltage, we get current through that nanopore, and when the DNA goes into the nanopore, it blocks some of that current, and we get a signal. As the DNA is moved through the nanopore by that molecular motor, the different sequences give rise to different signals. We get a current trace, and that's the signal that goes to the instrument. When the DNA has finished, it self-clears, which allows the next strand to be read. So one nanopore can produce a lot of data, but obviously the more nanopores you have, the more data you have, and so we have created an array. Currently, the arrays work by having an individual fluidic compartment for each nanopore. So this sits on top of our sensor chip. At the bottom of our sensor chip is our proprietary ASICs that we've designed to take that nanopore signal and pass it through to our instrument, where we can perform the next step of the process. And that is to basecall, because the nanopore signal is too difficult, too complex, too information-rich to read by eye. We need an algorithm. We use a machine learning algorithm to decode that signal, and that gives you the sequence that you use in your experiments. So that's very much a kind of under the hood view, but what does it mean for you? How does it really benefit your experiments or workflows? Well, the first thing to say is that our approach is high accuracy and output. We have achieved very high accuracies in the last couple of years. We are over Q20 raw read accuracies, which is over 99%. And we also can achieve very, very good consensus results. We can get Q50 on circular bacterial data sets. So that is pretty routine for us now. I would say that if you do want to have a fair evaluation of our platform, do make sure you are looking at the latest chemistries, base callers, and protocols. Another thing is the output, and we are a very high kind of data output technology. An individual flow cell we've managed to get 242 gigabases out of. I'll talk a little bit more about the PromethION outputs later. So lots of data. We want it to be as useful as possible, and we believe it is. We believe we have a very information-rich platform. And one way to think about this is in terms of the longest read. We know that single molecule, high accuracy, ultra-long reads are incredibly useful to you in order to solve really, really cutting-edge biological problems. And our read length record is an amazing 4.2 million bases in a single read. The community record, I think, currently still stands at 2.4 million bases. And we've also got an ultra-long kit, which came out a while ago, which will allow you to push those numbers up. Another feature of the platform is it can see modified bases. And this is an innate part of the signal. We just need to work out how to decode it. And we've made some great strides in the last few years doing exactly that. Our methylation numbers are looking really, really nice. Stu's going to talk about that a little bit later. And because we are single molecule, we don't need labels, we don't need amplification. We can look at RNA directly. And I believe we're the only sequencing technology that can look at RNA without turning it into DNA. And that means we preserve a lot of those modifications, and there is a growing interest and a growing community of scientists that are looking at the biological relevance of those modifications. So a very information-rich platform. It's also very versatile. We can use the same chemistry. A lot of people start on MinKNOW, and we can take that either to very, very large output devices such as PromethION, or very, very cheap, easy-to-use devices such as Flongle. So incredibly versatile. Also, time to result is a big one for us. We have very quick library preparation kits, kind of 5 to 10 minutes. We can take the sequencer to the sample because of the way we set up our technology. And that obviously cuts down your time to result and allows you to get to places where you may not be able to take a regular sequencer. And because we are electronic, we can make our measurements, and we can base call them, and we can pass those back to you in real time, which allows you to do bioinformatics while your run is still progressing. So all of that helps with time to result. So previous talks, unfortunately, we only have so much time to talk to you today. But if you want to delve a little bit deeper, then I would recommend taking a look at our website. That's nanoporetech.com and the Resource Center. And here you will find the company talks, but also a lot of talks and useful videos on how to run your Nanopore sequencer. So moving on to the platform section of the talk, PromethION. PromethION is an instrument that is designed with flexibility in mind. The idea is that you do not have to batch to run PromethION. If there is a flow cell already being run on your PromethION instrument and there is a free slot, you will be able to add in a new flow cell and kick off your own run without interrupting the other run. That's a deliberate feature of the technology. However, every now and then we do like to load the box up with 48 flow cells and kick them all off at once as a big batch. We do that as a benchmarking experiment, really to see how far we can push the technology. And we last did this in December, or late November, and we managed to achieve a whopping 10 terabases from a single PromethION instrument. We believe that's a record. It's certainly a record for us. Individual flow cells perform really well. So we ran 6 different human samples on these flow cells. 48 flow cells, a median of 208 gigabases, and our maximum at 242. So we were really impressed with that run. Lots of output. But we also know that people use the PromethION in different ways. And if we think about that in terms of a kind of production or factory kind of setup, you may want to add your sample to your flow cell and walk away from it. You may not want to interact with your run once you've started it. And so we benchmarked that, and for that we opted for a 10 kilobase N50 library, and we ran that out over 96 hours, and we managed to get 220 gigabases from that flow cell. If you want to go a little bit longer, then we also ran a N50 of 30 kilobases, and that also achieved 220 gigabases of output, but we needed to interact with that sample, and we did 2 washes. But for some people, those ultra-long reads are really the important thing. That's really what you're after. Then you can achieve really high outputs with N50s over 100 kilobase using this platform. You do need to nurture your run a little bit more. So here we got 100 gigabases from a single flow cell, but we did 4 washes. And you can see the outputs in the graphs and the read length distributions from our benchmarking. Obviously, benchmarking is a useful tool, but it's not the be-all and end-all. What we really want is for you, the Nanopore community, to experience those improvements, those developments that we've worked so hard on. And it's really nice to see positive news coming on Twitter. So a few examples on this slide here, including a new flow cell record, beating our internal record. So congratulations to Novogene. They've achieved 245 gigabases from a single flow cell. So talking about something slightly different on PromethION now, and that is accuracy. So it's important to note that over the last 2 years in particular, we have seen a real jump in our raw read accuracy. We have gone from raw reads at 92% to over 98%. And those improvements have come from algorithm improvements. We have then gone on to add chemistry improvements, but just on the algorithms, we've had a massive jump in raw read accuracy. And what we noticed when we started seeing these accuracy improvements was that MinKNOW was actually doing better than PromethION, and it really shouldn't be that way. PromethION is a next generation ASIC. It's one on from MinKNOW. It should have a better signal to noise. So we took a look at this, and what we saw was that some of the noise from the instrument was actually propagating onto the chip through our ASIC. And here you can see a chip layout where the electrodes labeled 1, 2, 3, and 4 across the power rail in red, and that's picking up some of the instrument noise. So what we did a few years back was we relayed out the chip. This was fairly early on in the PromethION story, and so all of the latest flow cells, everything that you have nowadays, is on that latest design. And what we saw was that we removed that kind of ceiling of accuracy on PromethION, and we got back up to comparable to MinKNOW levels. So that was all well and good, and that's what you have currently. But the algorithms group keep getting better at algorithms, and that means that they have pushed the raw read accuracy up again. So when combined with the chemistry, this is allowing us to get to really quite high accuracies. And for those people that are after the absolute top-end accuracies, you will start to see a slight limitation from your PromethION instrumentation. So we've redesigned the PromethION electronics with accuracy in mind, and on those electronics, we can achieve our best ever accuracies. In fact, PromethION, in terms of signal to noise, is better than MinKNOW and GridION. With these changes, we can achieve modal raw read accuracies of 99.3. So hopefully, that gives you some context as to why we're going to be making some changes to the PromethION instrumentation, and Rosemary will talk a little bit later about how we are going to roll those out. So moving from big to small, Flongle. The Flongle product concept is pretty simple. It's take all the expensive bits, put them in an instrument, and then the flow cell, the disposable part, can be as cheap as possible. And we also want it to be easy. We want cheap and ease of use to allow people to do more and more sequencing. So a cheap flow cell concept also has to be high volume, and the engineering teams have had a great 6 months working on improving our production outputs. They have automated more and more parts of the process, and they have improved the cycle times of existing processes. We've also introduced a lot of inspection, which will improve our outputs, but will also improve the consistency of the flow cells we generate. And that consistency should turn into more stability in your hands. In terms of unfinished business on Flongle, there are two things. One is the cheapness of the flow cell. So that flow cell still contains a silicon component to it. And that component is really, it's a hangover from the MinKNOW days when we were prototyping. MinKNOW has this component, it needs it, it's higher channel density. Flongle doesn't need it, we can go to cheaper manufacturing options. So this is what this project is. The team have really been pushing this over the last 6 months. We can go to plastic substrates now without the need of silicon. And that is in reasonably early stages. It's still in R&D. We have to up the channel numbers, but we can still achieve some really good outputs from our prototypes. A good point here is that the Flongle chip is the same format as the silicon in terms of geometries, and that means it will fit into existing flow cells. So we can run these on our normal Flongle adapters, and you will be able to too. A Flongle adapter will take either a silicon or a plastic, it doesn't matter. On the prototypes, we've managed to get a gigabase out of a single flow cell, so that's a really good mark to hit. And a bit like PromethION, we've also been looking at the chip and the platform and the instrumentation with an accuracy perspective. And there are a few improvements we've made. The plastic is better than silicon. Plastic is a better insulator. That means it's lower noise, so that's going to help. We've also changed the metal layout to reduce the amount of metal in the sensor area, and so that should also benefit our accuracies. At the moment, the plastic chip gives you a slight accuracy improvement on the current Flongle if you're running kind of baseline R9 chemistries and Kit 10. However, when we move to the kind of Q20 chemistries and algorithms, that's where we're really seeing the difference. So right at the top end again, these improvements will allow Flongle to be as accurate as MinKNOW. So the other piece of unfinished business is to remove the flush. So at the moment, users have to flush the mediator out of the system before they add their sample. We'd really like you to be able to just add your sample into your flow cell and press go. The mediator is there because our electrochemistry relies on platinum. That's easy to manufacture, but it's not very good electrode material. So we have a mediator to make it fast. We need that if we're going to use platinum. So we've been looking at a different electrode material, and that is silver. Silver is routinely used in things like electrophysiology by the academic nanopore community, and also in things like glucose biosensors. And what's great about it is it's very fast and stable. It can hold a really stable potential without having to use a mediator. And so in this system, you should just be able to add your sample. So early looks for us on silver, but early data is looking quite promising. We can hold a stable potential for a lot longer than platinum. You might notice that MinKNOW does change the potential over time as you do your run, as you consume mediator, and eventually your well just dies. Well, with silver, we've got some wells which are running a lot longer than mediator wells. We've got to 30 hours, so we're pretty impressed with that. That could turn into an output improvement. And also in terms of accuracy, the silver system is looking pretty good. So normally we have to optimize that accuracy with run conditions, and we have to train base callers. But this is it's fairly recent data, so we haven't had a chance to do that. And here you can see a pretty respectable raw read accuracy with absolutely no optimization. So we're looking to see how far we can push this in the next few weeks. So a project I'd like to finish on is the voltage sensing project. And it really serves to illustrate just how much data you can get off a Nanopore platform. And as you've heard, a lot of the talk is about the need for these mediators, these wells, and they really do hold the technology back because we're detecting current, we need these independent volumes. Well, voltage sensing is a paradigm shift in terms of how we're detecting current. We're still detecting the same signal, but we're doing it by looking at a very local perturbation to a field. And this means we can pack things in very tightly. So for a MinION piece of silicon, our maximum kind of theoretical output we think is to get 100,000 channels onto that piece of silicon with a border for some common components. And that would be 3.9 terabases a day from a single flow cell. So perhaps more realistic numbers would be to assume 60% pores, 60% pore utilization. That would still give us 58 gigabases an hour from a single flow cell. Optimized, that could be 600 bases a second, 80% pores, 80% utilization, and that would give us a 10 terabase output over a 3-day run. So that's equal to a fully loaded PromethION, but only using one flow cell. A different way of looking at those numbers is that a single flow cell would be capable of sequencing an entire human genome in 60 minutes or under an hour. And a third way is that if we assume a $1,000 per genome cost, $1,000 per flow cell cost, that would equate to a $10 human genome, just from a flow cell perspective. So that wouldn't include things like the extraction, library prep, or Basecalling, but it does really highlight just how cheap nanopore sequencing could be from a platform perspective. So how are we doing on that? Well, we've had a really strong 6 months. Last time I spoke to you, we had built an instrument that could record voltage sensing signals. It was a bit noisy, but it allowed us to do membrane information, pore insertion, and actually achieve a squiggle from the voltage sensor. That looked very much like our current sensing, which is obviously what we want. So that was very encouraging, and it really unlocked the next part of the project. So in this phase, what we're doing is we're taking it all the way through to base calling, and we're learning a lot about the system and the ASIC and the electronics we need. So 3 things we need for that. We need these overhang structures, because we're getting rid of wells in this design. They are coming along nicely. We can get good optical data off those. And that's also a project we're interested in using for PromethION as well. We need a middle layer. This is something which is new on the voltage sensing chip, and that is for each nanopore kind of pixel to have a fluidic resistor. We have a few designs. Those are coming along well with our MEMS partner, and we are looking to integrate those into the rest of the chip. And last time I spoke to you, we had not received our ASIC, but late in December, we did get our hands on our prototype ASIC, so that was a really nice present. We have a small number of channels on our prototype ASIC. It is there for us to learn about the functionality and the kind of layout of the circuit that we need to inform us on our product ASIC design. So over the next 6 months, we are going to take these 3 layers, integrate them together. We are going to build a breadboard instrument. We're going to get MinKNOW to pull the strings on that, and that will allow us to collect some nanopore data. Once we have that data, we can train a model. And so hopefully, the next time I speak to you, we would have achieved that, we would have trained that model, and we'll be able to use that to base call our first data from our voltage sensing project. So with that, I'd like to thank you for your attention and move on to the next speaker. Thank you.
Hi. I'm going to talk to you about base calling, about accuracy, and then a little bit about software features and usability. So base calling first. Most of what I'm going to say is either just released or about to be released, so very much this is what you can do now sort of talk, although a few more forward-looking bits sprinkled in. So when we talk about base calling, we're thinking about the nanopore signal. And on the surface, that signal is very simple. It's a one-dimensional time series of current measurements. But the signal is affected by quite a lot of things. So it's affected by all the bases in the pore and many of the bases outside the pore. It's affected by what's going on in the enzyme and how the enzyme and the pore sit together, and the temperature and the chemical environment, all sorts of things. And when we base call that signal, we employ recurrent neural networks to decode that signal for us. And we've been doing that for a few years now. The latest base callers, combined with the latest chemistry, now hit a raw read accuracy in excess of 99% single-pass raw read accuracy. And of course, you can see base modifications directly in the signal. So if we step back and we look at just the base callers alone, we can see with our R9 chemistry, in the last 2 years, we've improved the raw read accuracy from 90% to 98%. That's a 5-fold reduction in error in 2 years from algorithms alone. So that means if you have old nanopore data lying around, then it might be worth digging it out and recalling it and seeing if you get a more accurate answer today than you got back then. So here are the new base callers. And back in December, I spoke about our research base caller, Bonito. These architectures are now fully integrated into Guppy and MinKNOW. We have 3 models. We have the fast base calling model, which keeps up on all ONT devices. That's now achieving modal accuracy nearly 96%. We have the high accuracy base callers, which is a good balance of performance and accuracy, and that's nearly 98%. And we have a new super accuracy model, which is the standard architecture from our Bonito research base caller, and that's achieving 98.3%. We can see at the top end, R9 and R10 both achieve those top end accuracy numbers, but we have a little bit of work to do on the fast and the high accuracy models for R10. But you do get consensus benefits. Before I talk about that, I'd like to talk a little bit about modified bases. And with Nanopore, you can directly see base modifications in the signal. We and our users find that Nanopore is more reproducible, less biased, and reaches parts that other technologies cannot reach. You also get those per-read long-range connections. And we're working hard to make this a mainstream thing. And that's a community-driven effort, and we're working on standards, we're working on genome browsers. So a few shout-outs here to James Bonfield at Sanger, who's leading the standards effort, and Colin Dayesh at UC Berkeley, and Jim Robinson at UCSD, who are leading the genome browser efforts. And here I'm showing a screenshot of a JBrowse prototype, and you really can see those long-range connections. So on to high-level accuracy and consensus. Now, when we talk about consensus, usually we show these plots of depth versus consensus quality, but we don't worry too much about the assemblies themselves. So we've taken a step back from that. We're Nanopore, we have long reads. Let's see whether we can get fully circularized, contiguous, accurate, complete bacterial genomes. And we can. And the numbers are pretty much in line with what we show on our standard benchmarks. So that's reassuring. So here are those benchmarks. And we're going to offer consensus polishing models for all our base callers. Here you can see that the more accurate base callers deliver you better consensus accuracy. And you can also see the benefits of R10. A lot of genomics is about variation with respect to a reference genome. And when we talk about human variation, there are three sorts. There's the SNPs and indels that are the small scale changes. There are structural variants that are larger scale changes, and there are the base modifications. And with Nanopore, you can get all three types of variation from the same run. Although I should note these benchmarks, the modifications are a different genome because of the availability of orthogonal data. And we see high SNP performance in the high 99s. These are not the top end numbers you can achieve. You can do better with deep variant. I'll refer you to Kishwar Shaffin's talk, where he talks about his pepper margin deep variant pipeline. You can get all the 9s there. We have top end structural variant performance over 96%. And we believe we are the gold standard in epigenetic modification detection. Human sequencing is also about de novo, and with Nanopore, you can get contiguous, complete, high consensus accuracy human genomes from one or two flow cells. And when you combine Nanopore long read data with Nanopore PORE-C, which is our chromosome contact capture technique, you can see we get fully haplotype resolved assemblies. I will refer you to our apps poster for more details there. No discussion of accuracy is complete without barcodes. Barcoding with Nanopore is very accurate. False classification rates down to 0.002%. So you can mix samples together with confidence on a flow cell that you can demultiplex them, deconvolute them afterwards. We do have a chemistry update. We call it our Q20 Chemistry. And this is a relatively small improvement on what we currently have. It's a new motor, it's E8.1, and it's a bit slower. We've optimized several aspects of the system around that. It's compatible with R9 and R10 flow cells, and we can see that with the Q20 chemistry, we're now achieving raw read modal accuracies greater than 99.3%, which is in excess of Q20. There is a Q-scale plot there for those who like that, and we think the pileups are looking pretty tasty. The Q20 chemistry has been with our developers for a few months now, and we're seeing good results from the field. We're really building confidence in that chemistry, and we'll be moving that into a broader early access phase. And what we find with the Q20 data is that the base calls are now at the level of accuracy where downstream tools start to just work. So that removes your dependence on these more complicated deep learning models for variant and consensus calling. And we can see that with Longshot, which is a SNP caller, we're getting 99.7% F1, really high accuracy there. And consensus, we're getting Q50 down to 10x depth. So accuracy summary, raw read accuracy 99.3%. SNP detection at 99.9%, that's a deep variant number. Assemblies, complete, contiguous, accurate, top-end SV performance, and the gold standard for methylation. You couple that with the platform benefits, 10 terabase outputs from a PromethION run, over 240 gigabases from an individual flow cell, and read lengths up to 4.2 megabases. So I'd like to talk a bit more about usability and software features, and A lot of our efforts there are focused on bioinformatics. And one way we can make bioinformatics more usable and accessible is by packaging up workflows, and we can deliver those via Epitome Cloud. So they're real-time, end-to-end workflows. There's a wide range there, intuitive, GUI-driven, really accessible. We're also integrating Epitome with MinKNOW, our sequencing software, so you can launch those Epitome workflows with your run and get those live results back into the MinKNOW UI. Here's a screenshot from our latest development work. And we have the more tightly coupled on-device analysis, things like barcode demultiplexing and reference alignment. They're fully integrated with MinKNOW. But bioinformatics can be as much about data exploration as it is about running those pre-canned workflows. So we have our research software tools available on GitHub. The Epitome Labs team are here to help with tutorials and workflows that will help you learn those bioinformatics skills and explore your data and maybe customize a workflow for your particular application. Our sequencing software, MinKNOW, is designed to integrate with your existing lab environment. So the MinKNOW APIs are there for full run control and tracking integration with your lab information system, your LIMS. We understand that many labs don't have a LIMS, so we do offer a simpler version, which is spreadsheet-based. So we have a CSV sample sheet upload, and a new feature there is you can now assign an alias to each barcode, so you can embed your per barcode sample information directly into the run data, and that will simplify things downstream. Adaptive sampling is a feature that is unique to Oxford Nanopore sequencing. You can sequence the first few bases, decide whether you like them or not, and then spit out the read if you don't, and grab a new one. With adaptive sampling, you can get up to 10 times enrichment, but in more typical use cases, you can see maybe 4 or 5 times enrichment. And that's a function of read length, the proportion you want to enrich for, and the various decision times and reload times. Enrichment depletion is fully released on GridION and MinION. There is a beta release for Mark 1C. We're working on barcode balancing features. They'll probably come to GridION first, and we'll move the Mark 1C beta into a full release soon. If you want to do something more complex, you can roll your own analysis with our API, and there are a few community tools there to help you get started. There's ReadFish from the Matt Luce lab, which is basecall driven, and there is Uncalled from the Mike Schatz lab, which is signal driven. The MinKNOW mobile app is available in Apple and Android stores, and that gives you the full feature-rich UI on your mobile or your tablet, and that's great for demos and teaching, or if you just don't want to leave your desk. That gives you the visibility over your local network, and we are working on secure internet remote viewing. Now, I mentioned the 3 base calling models, so that's a choice you can make at runtime or in your post-processing analysis. And you can choose in the UI which base call model you want. Our fast base calling, as I said, keeps up on all ONT devices. High accuracy is about 8 times more intensive than that, and super accuracy a further 3 times more intensive. But fast base calling today is as accurate as high accuracy base calling was 2 years ago. So we're going in the right direction. Of course, we understand that everybody wants the most accurate base calling, so we're re-enabling cloud base calling. This used to be the only way to do base calling back in the early days of our MinION Access program. So this will be an Epitome workflow, and as well as leveraging the power of cloud compute for your production base calls, it will also make it much easier to run our research base callers. We're working on an updated laptop specification, which includes GPUs. It's not quite ready yet, but until we release that, I highly recommend reading anything that Miles Benton has written on our community or elsewhere on this subject. Thank you very much, Miles. That's great stuff. We're also working on speeding up those algorithms and making Guppy just work with whatever GPU you have available. I'd like to signpost a few features that are coming in the future. We're working on attaching network storage or cloud storage and making that easier, caching the credentials, things like that. And we're also improving our integrations with your Nanopore My Account. That will allow us to add a bit of security around logins, as well as making it easier to do things like offline device activation and potentially providing that route to internet remote viewing. With that, I will hand over to Rosemary. Thank you very much.
Thank you, James. Thank you, Stuart. I'm now going to talk to you about how we take all of the innovation from our research teams and our development teams and bring them into your hands. We categorize our products into 3 different types. We have preparation products, sequencing products, analysis products. We have to cater for users who want to use the product in fields, all the way through to really high throughput automation environments. On the sequencing side, we have users who want maximum outputs and really, really high vast amounts of data. And we have other users who want small, simple little experiments. On the analysis side, some of you want to really get into the code and really help us develop the next solutions, and others want to click a button and get an answer. And what we've really enjoyed doing over the last few years is working with all of you, from the Arctic to the sub-Saharan deserts, in caves, out of caves, in labs. We've really, really enjoyed working with the whole community to come up with the solutions that we've come up with. Now, around our philosophies to bring products out, of course, we've got a really great core technology that enables so many new applications. Alongside that are 4 core values. We want to make accessible technology. We want it to be capital free. We want our pricing to be transparent and fair. We want our users to come along the journey, the innovation journey with us. So we want to make upgrades and keep the upgrades included in the platform. And we want to really, really engage with the community and build the next product of the future. So onto that capital-free model, we have scalable, all of our scalable devices, our technologies scaled across from Flongle all the way to PromethION. And all of these devices are available as starter packs. So this means that you're buying consumables, you're buying flow cells, you're generating gigs of data for MinIONs, Flongles, GridIONs, you're generating terabases of data on PromethIONs, all for that initial purchase of consumables and kits. All of our users use the technology for different things. Some users want it for simple amplicon sequencing. Others want to run whole genome, high throughput runs. Others want to go ultra-long and really, really push the boundaries of the technology. So what we've done is developed a system that has high data output capacity, and then it's down to our users on how they want to deploy our product and what they want to get out of it. Irrespective of if you're running something and generating something like 10 gigs on a MinION, or really, really pushing the throughput and getting up to 30 or 40 gigs, irrespective of where you are getting very competitive price per gig per flow cell. For those users on PromethION who are at the sort of breaking the 100 gig into the 200 mark, as James has spoken about, then you're talking about $3 a gig pricing in that range. So our pricing is all transparent, it's all in the shop, and it's very, very competitive. Regarding our continuous improvement, we keep innovating, our products keep getting better. Anyone who started with us all the way in 2014 started with the MinION, the early access MinION, they then upgraded it to a Mark 1 and then a Mark 1B. Lots of those users then went into minutes, and now they're getting upgraded into Mark 1Cs. And that same journey is happening across all of our other platforms. But it's really important to remember that actually the biggest difference actually comes from the sequencing chemistry that we ship in our flow cells, the kits, the enzymes that we make, and the software. So a user who will have bought a Mark 1B in 2016 is now getting an enormous amount more data and much, much higher accuracies than they were all the way back then. And this is why we develop the product in the way that we do. We want you to come along with us and come with us on the innovation journey. But we do understand that there are some users who really want to be able to plan their experiments well. They need to know exactly where things are. And for anyone who's sort of built teams, you've always got that sort of whole process at the start where you're kind of forming things and then you're sort of brainstorming things are coming together. Then you're sort of normalizing, and then you get a really performing team at the end. And it's quite similar for our products. And to help you and to guide you with where the product is on that journey, we'll be labeling up in our shop products that are developer access only, so you need to are available only upon request. Products that are in early access. Now we may be in open early access or a registered shop. Then the products get into a released phase, and then fully released. And the main difference there really is the warranties that we're giving, change notification that you get, so that you can more adequately plan your experiments and plan your projects. Also regarding that communication back, we have updated the new feature request pin board. This is now live in the community. It lets users put their feature requests in. You can upvote, you can comment on other users' theories and thoughts. But the main reason that we've done this upgrade really is because it has an improved backend that more closely communicates with the development teams. So we'd be more responsive, we can get better insights, and develop better products for you. All of the existing requests that were in the previous system have been migrated over, so don't worry if you have been putting in ideas with us. They are still there, still captured, so please do go and explore the new feature request pin board. So moving on from how we actually sort of bring our product to market into bringing you the latest updates from Oxford Nanopore. So on the sample prep side, I wanted to start actually with a huge thank you for everyone who's been working on COVID for the last year. We've had really such an immense connection and big community effort really going into sequencing all of these COVID genomes on Nanopore technology. What we've been doing at Oxford Nanopore is making sure that, that you've got everything you need. So our teams have been focused really hard on getting all the ligation chemistries, the barcoding kits, all of that has been scaled up to make sure that everything is in stock and is there when you need it. We brought out the AMX2 kit, the expansion pack that many of you were needing to get the most out of your barcoding kits. And of course, things like MinIONs and GridIONs are in stock, so anyone who's new, who wants to get started now, can do that really, really quickly. With the release of the Rapid Barcoding Kit 96 at the start of this year, that's given us an opportunity to make it simpler. So we will, of course, and are continuing to support all of the Arctic Classic methods, but with the Rapid Barcoding Kit, the 96 version, you can now deploy the midnight whole genome sequencing and also a spike gene sequencing protocol that's been developed. This lets you get much, much faster turnaround times, a much reduced price per sample. There are not as many third-party reagents involved here. And when you pair that with the Epitome Arctic pipeline that was released earlier this year, it makes a much, much simpler user journey. We do have a lot of users coming to us as well and asking us to provide everything from one single source. So to that effort, we've been working with NEB and IDT, and coming soon will be RT-PCR expansion packs that have the RT-PCR enzymes, and also either the midnight primers or the spike-seq primers, depending on what you want to use. And when you buy that in combination with the rapid barcoding kits, run it on one of our sequences and analyze it on Epitome, you should have a robust and easy-to-use workflow for anyone who is now getting started on the COVID sequencing. Internally, we've continued to work on and develop our product, our VolTRAX product for SARS-CoV-2. Last time we spoke, we were showing you early results from development. This product has actually now made it into the hands of developers in fields. Users who are right in the middle of the COVID pandemic are running this and evaluating it to make sure that, that it's meeting all of the needs and the requirements. To do it, of course, it means that you need a PCR-capable VolTRAX. And so to that end, we've done it. We're there now. This is VolTRAX V2. It's correctly calibrated to perform the PCR. It's compatible with the current black cartridge, and now this new blue cartridge that will be coming out. So the upgraded blue cartridge it's an improved construction for high heat applications. It's got an integrated priming fluid, so it's just a simple twist mechanism for you to prime your cartridge array. We're initially selling it programmed for RT-PCR SARS-CoV-2, but of course other RT-PCR methodologies are in development. To get your V2B upgrade, you simply need to register your interest. The team will come back to you, will dispatch a new V2B, and your old VolTRAX comes back in return. So we are now enabling VolTRAX for PCR. Regarding the rest of our preparation methods, really of note has been the release of the ultra-long read kit that happened earlier this year. We are really, really excited to see everything that the community has been doing with this kit, all the way through its sort of developer phase that we had earlier. There are so many talks, so many posters, so many tweets of people doing incredible things with these ultra-long reads. And what we've been doing on the side, of course, is also updating our Nanopore documentation center to make all of these protocols much more visible, much easier to find. And of course, if you do have feedback and do want further improvements made, do connect with our team, do talk to them. Other kits that have been in the pipeline for a while, whilst our team have been focusing on supporting the COVID effort, have been the native barcoding kits, the Kit 10 versions of native barcoding kits. These are now getting ready to come out. And what we're going to be doing, and we're going to change things a little here, so we will be bringing 24 barcodes into one kit, but also combining that with a sequencing module. So you no longer need to buy different kits to get what you need. So these will have the fuel fix adapter in, of course, 24 barcodes in a kit. We are putting ampule beads inside and including the sequencing chemistry. After this 24 kit comes out, the 96 will follow. And this is same again, same chemistry. And what we will be doing here is moving to a single-use plate. A lot of the feedback has come, it's much easier to use single-use plates. And so we will be bringing that to market later in the summer. The Q20 chemistry, very exciting, of course, lots of tweets, lots of developer use, and of course you've heard the talks from James and Stuart before me. The Q20 kit is essential to get that 99+% accuracy. So it's a kit with fuel fix adapter. It's got a high capture adapter in there too, the Q20 motor, and all of the other ligation sequencing kit components. Now with this new kit comes actually a huge amount of options. So what we will be focusing on internally is your R9.4.1 with your Kit 10 options. We are focusing R10.3 alongside Q20. The other options are compatible and they do work, but those two are the ones that we're focusing on just for clarity's sake. If you want to register for Q20, you can just go to our website. Please do register for the early access program that will be starting shortly. Now, Gordon mentioned at the start of the session that we have an increasing number of very large genome projects happening on the platform. And those customers are asking Oxford Nanopore for two things. On the first hand, they want automation, they want high throughput workflows. On the other hand, they want to take the most and get the most out of the output improvements that have come from PromethION over the last few months. And they want to start sequencing 2 genomes in a single flow cell. For that purpose, we are going to be combining our 96 native barcodes with our XL library kits. So this means that you will be able to start with your 96 samples, adapt them, pool them, and run a single P48 from that single workflow. On the automation side, our team are continuing to grow internally. We have the capability to develop methods on Opentrons, on Hamilton. Agilent is coming online now. We also have a lot of feedback from users that they really want an automation-friendly method of priming and loading flow cells. And to that end, our engineering teams are working hard on integrating our flow cell loading with automation platforms. Now onto our sequencers. MinIONs and GridIONs have been at the heart of a lot of work that's been going on this year and last year on sequencing COVID. So I wanted to talk a little bit actually about Flongle. Very versatile platform, small genome, targeted sequencing, library QC. We are seeing now improved robustness in field thanks to the work that our teams in production have been doing. And another part of feedback that we often got was that when you loaded your Flongle, some of the pores didn't stay where they needed to. We found that if we placed all of the reagents and placed the flow cell loading reagents in glass vials, this actually really helped to mitigate the issue. So the glass vial kit is shipping now. And also customers who want to do rapid tests, which makes perfect sense on a Flongle, also needed to see an improvement in performance. And we've now seen that with cleanup steps before you load, you get that performance back. So to package all of these improvements up, we've moved to a pack of 12 flow cells. This better matches the glass vials and makes that whole ordering process much easier. We've reconfigured all of our protocols to improve our library utilization, and also the product is now fully in stock. So we do really look forward to getting a lot more user stories from the field in Flongle, and we're actually very excited about some of the work that's being done on it right now. Regarding PromethION, our high output platform, you've heard from the team that we have been continuing to improve our chemistries, continuing to improve our algorithms, now to a point that a PromethION with its current hardware is supporting R941 chemistry accuracies of 98% and above. The R10 implementations of accuracy do need a hardware upgrade, as you saw from James's talk. So with these latest accuracies that are now over 99%, what we will be doing is performing a PromethION upgrade program. So you need to contact, if you have a PromethION, contact support, register your interest in running the Q20 chemistries on your device. This will need an open order for flow cells and an active software license. The team will go through that in more detail with you. And you will receive then an estimated timeline for your device upgrade. And we are really, really looking forward to seeing a lot of you take this offer up and get to really high accuracies and high outputs on the PromethION platform. Regarding then the sequencing anything by anyone anywhere, a lot of that actually language comes into it. We have users all over the world, and we've started to translate some of our documents, but we're really excited now in the next release of MinKNOW to have a Chinese UI. And this, of course, is just the start, because once you go to for one language, you can go for many. And we do look forward to working with the community as we implement new languages on our systems. So finally, on to analysis. You've heard from the team, there are now quite a few configurations to run, but it's important to remember that Oxford Nanopore ship all the different base caller models on all of our software. So you have the fast models, the keep-up models, you've got the high accuracy models, the super accuracy models. And so as a user, you choose your flow cell, you choose the kit chemistry that you run it with, you select your model, and then you get an accuracy out. Our fast base callers have all been upgraded, so they're all touching 96% now. And so that means that a lot of users who need quick results, keep things up to date, can really get a lot more biology done. And Stu also covered all of the consensus performance on those latest updates. Users who then want the higher accuracy models, they run the devices in what's called catch-up mode. There are some users for where they have more samples to process than time to wait for the catch-up mode, and for that, we are pairing up now with NVIDIA. Oxford Nanopore will be a distributor for the NVIDIA DGX Station A100. So users who need extra compute can come to us, and we'll work with NVIDIA on making sure that you've got this new standalone device providing 2.5 petaflops of compute at a very, very reasonable list price. So do get in touch with the teams if that's of interest to you. On the Epitome Lab side, again, Epitome Labs came out roughly a year ago now. This is a method for us to put together all of the tutorials that you need in order to get the same SNP numbers that we do, or structural variants, or methylation. So we have all of these tutorials about how to handle our data. And it's great if you're new to bioinformatics, you want to get to know how to do things. It's been really, really a great tool for those users. Now, there are some users who really like the results, but want to scale it, and they want to run this on multiple genomes at the same time in their own centers, and this just isn't the right solution. So the Epitome team have been working on Epitome workflows. So these are containered. They're in something called Nextflow, and it scales your analysis, but it uses all the same tools that are in the tutorial. So there's not a black box. You still understand exactly what's happening to your data. Then regarding the cloud, you can take these containers and push them into the cloud. So you should start to expect to see things that start as tutorials, making into workflows, and workflows getting into a cloud informatics. Again, it's all the same, it's the same pipeline as the tutorial, so you get to know exactly what's happening in your analysis pipeline. And then backed by popular demand is Epitome base calling. We see reams and reams of tweets of people who want the latest accuracy but don't have the right hardware, so it only really made sense for us to re-enable base calling up in the cloud. All you have to do is open your Epitome agent, select your files, they will go into the cloud, and fast queues will come back. We will be providing a lot more information at the time of launch about sort of all the fair usage policies that will come with this, but we're very, very excited to work with you guys again on bringing base calling back online. So in conclusion, Oxford Nanopore, we've come a another step further since we last spoke, with our raw read accuracies at over 99% now, our SNP scores continuing to be very, very high, and we have great assembly stats now on human. Bacteria have always been doing very, very well on. Structural variant detection, methylation detection, all of that information included in one read. And the read lengths can be really, really immense. We can do high outputs, we can do low outputs, and we just continue to enjoy working with you in bringing all of these latest features out to the field. And with that comes the slide that everyone in the Nanopore community loves and everyone at Nanopore loses sleep over, which is our Nanopore release plan. Here you can see that we're going to be focused on our device side, focused on the DGX station, the PromethION upgrades and VolTRAX over the summer, getting the PromethION R10.3 flow cells into the early access shops, and getting VolTRAX V2B cartridges out as well. On the kits, we have a whole slew of kits coming out over the next couple of months, and software as well. Guppy 5 is imminent with the Bonito CRF models, which will be in MinKNOW as well, epitome Basecalling. So it's all about packaging up those latest Basecaller improvements and then getting ready for that Q20 early access. And with that, I'd like to thank you for your attention. Stuart and James and myself will now be in the Q&A section, and we will really looking forward to speaking with all of you.